All right, thank you all so much for coming to the Natural Language Seminar today. I think we're going to go ahead and get started. I'm very excited to welcome our speaker, Julie Kallini, who is from Stanford. Julie Kallini is a second-year computer science PhD student at Stanford University, advised by Christopher Potts and Dan Jarafsky. Her research spans several topics in natural language processing, including computational linguistics, cognitive science, interpretability, and model architecture. Julie's work is generously supported by the NSF Graduate Research Fellowship, the Stanford School of Engineering Graduate Fellowship, and the Stanford Edge Fellowship. Before starting her PhD, Julie was a software engineer at Meta, where she worked on machine learning for advertisements. Julie graduated summa cum laude from Princeton University with a BSc in computer science and a minor in linguistics. So everyone, please welcome Julie, and I'm really excited for her talk.
Thanks so much, Katie, for the intro. And it's so nice to be here. I'm really excited to be presenting this work to you. So I'll be talking about a paper that I did in my first year of my PhD, Mission Impossible Language Models. That was presented at ECL this past August, where I got to meet Katie. And yeah, I'd like to thank all my co-authors, Isabel Papadimitriou, Richard Futrell, Kyle Mahwald, and my advisor, Chris Potts. So let's get started. Earlier this year, there was a short correspondence in Nature that made 3 big claims about why AI doesn't model human language. And I could talk at length about all of the claims, but I'm going to focus on this third one. Here, the authors state that large language models can produce impossible languages, or those not generated by the principles governing all human languages, just as well as, if not better than, natural language output, and cannot distinguish between them. And similar claims have been made by several linguists, including Noam Chomsky in his New York Times article from last year. So why is this important to us? Well, for these authors, large language models learn possible and impossible languages equally well. And so it follows that LLMs do not model the structure of human language and cannot tell us anything about language. It's kind of hard to articulate why they would think this isn't exactly the case, but this is a large part of the Chomskyan ethos. This claim, if true, would have significant consequences for linguistic methodology and also for the viability of LLMs as the basis of robust language capabilities. What we set out to do is actually put this claim to the test. So we trained some language models on impossible languages to observe whether they are learned just as well as possible languages. But first, what exactly is a possible or impossible human language? This question lacks a clear answer. But if we take the characterization of language as it's presented in much of theoretical linguistics, and this is the background for most of the critics of LLM, so I'll take their characterization of language, then all human languages are thought to have hierarchical syntactic structures generated through recursive rules. So you might be familiar with representing sentences through these hierarchical syntax trees. If we grant that possible languages are defined by these hierarchical structures, then what would the impossible languages be? Again, we lack a clear answer to this, but let's say that these are the languages that have the opposite type of rules, or rules that are not hierarchically structured. So more concretely, these might be rules based on the linear order of words or rigidly determined by word positions. The example I like to give is taking the same syntax tree that I showed before, and making an impossible language out of it by introducing a rule that violates the hierarchical structure of sentences. As an example, we can look at how tense is marked in the sentence. In English, it's marked by an S suffix. And what if the way English marked verb inflection was by placing the tense marker a fixed number of words later? This would be a completely systematic pattern, but no language uses counting and inserting markers in this way to signify verb inflection, and it's just completely unnatural. So what I just showed you was an example of a language that involves linear counting rules, but I think that this is a narrow account of what is impossible. In the paper, we tested a much wider range of impossible languages and placed them on a scale we call the impossibility continuum. So we know that real languages in the world are possible to learn, for humans to learn by definition, and they're hierarchically structured. the languages involving count-based grammar rules like the one I've shown before are close to attested languages. They're very similar to attested languages, but they include some rules that do not conform to the hierarchical structure of attested languages. And beyond these, we also test languages of reverse strings and languages with shuffled word orders. And in constructing all of these impossible languages, we consider both their information theoretic attributes relevant to machine learning, as well as their formal linguistic characteristics. And we signify the boundary between possible and impossible with a fuzzy question mark to indicate that these questions are currently fuzzy. This distinction is fuzzy. Our methodology can be used to explore this boundary for LLMs. So how exactly do we test whether a language model reflects the impossibility continuum? In our experiments, we create synthetic impossible language data sets by altering English data. For the base corpus, we use the 100 million word baby LM data set. And then we train a GPT-2 small model from scratch for each synthetic data set. So these models are not pre-trained. They've only seen data in the particular impossible language. Then we use test set perplexities as a general metric for the extent to which a model has learned an impossible language. And we look at perplexities over the course of training. So I'll first start with the first class of languages that we present in the paper, which we call the shuffle languages. These involve different shuffles of tokenized English sentences. So the first language, which we call the no shuffle language, is just the control. So this one represents basically unaltered English. All we do is tokenize it. And in all of the examples I show, the different colored blocks represent different GPT-2 tokens. So this model's test set perplexities form a baseline to which we'll compare all the impossible languages. The first real impossible language is the non-deterministic shuffle language. So this takes the input sentence or the input tokens and randomly shuffles them at a sentence level. And as you might expect, this language is more intuitively impossible. So its perplexities are much higher than the control language. Next, we have the deterministic shuffle languages, which are very similar to the non-deterministic shuffles. But in this set of languages, the sentence level random shuffles are consistent across sentences that have the same length. So in the examples that I have on the slides, they both have the same length, even though they're different sentences. The tokens get mapped to the same locations after the shuffle. And we created several of these deterministic shuffle languages by varying the random seed of the shuffle. And the interesting thing that we found is that all of these languages had better perplexities than the non-deterministic shuffle. This might indicate that the language model was able to leverage some consistency with where the shuffle tokens end up after performing the transformation.
There's no relationship. Is it okay to interrupt?
Yeah, absolutely.
There's no relationship between the permutation of a shuffle of length K and J, right? Like,
yeah, there's no
random for every one of the lengths that you're going to support.
Exactly. I guess empirically, there are certain token sequence lengths that are much more common than others. So like, I guess sentences of length 10 in the BPLM data set are like very common versus.
These are all autoregressive models, so they don't even know how long their sentences.
That's true. Yeah. So there's added uncertainty just because it's autoregressive.
And yet, it's actually kind of not even surprising that it would be better.
Yeah, I think that this is kind of surprising. Yeah, this is definitely surprising to us because, you know, being able to pull any random word almost sounds easier than having to predict this next token that is a very specific word, like that you could technically figure out, but it's by this very specific complicated rule. Almost sounds harder to do, comparing the non-deterministic to these deterministic shuffles.
But it also depends, like, what does perplexity of 575 compared to 550, for example, tells you, right? I know that
It's all very confusing.
it's all very confusing. Like you have a better, when it's sort of deterministic, you have a better chance of like whatever you said. This is the most probability, like actually being according to that shuffle. Then, but it's also like I think perplexity is hard to interpret in a way. like,
I think
it's
that's fair.
bad, it's like,
I think that's fair. Yeah. I think that, well, these perplexities are quite actually large in difference compared to, like, I guess, I think there have been like more fights over smaller differences in perplexity in NLP. Yeah, I agree. It's like a coarse grained metric. We go deeper into a particular set of languages that we think are more interesting and do more targeted evaluations than that. And the whole question of how to evaluate these things has been something we had to think about and are continuing to think about more. All right. The next shuffle language I have is the local shuffle language. So here the tokenized input sentence is deterministically shuffled in local shuffles of a fixed window size. So in the example I have on the slide, this window size is 3 tokens, but we can vary this to create different local shuffle languages. And with a window size of 3, the model's perplexities come like very close to the control model. Still higher than the control model though. And if we make this window size larger, the perplexities go up. So here we have a window size of 5 and a window size of 10. So this kind of shows that the language model leverages the like locality of natural language in a way, so it's able to learn smaller local shuffles better. The last oddball kind of language I have is the even odd shuffle. So this is just taking all of the even index tokens and placing them before the odd index tokens. And this language had perplexities like very similar to the local shuffles, which is strange, even though they can create these long distance dependencies. So this is kind of an oddball language that I'm trying to understand. So these are all the shuffle languages. There's also a set of reverse languages in the paper that I'm going to skip over just for the purpose of getting to the last set of languages, which we call the hop languages. So this class of languages is exactly the type of language that I motivated at the beginning of the talk. It uses count-based grammar rules. So again, we have a control language that represents English, basically. So this is the no-hop language. To transform this for our experiments, we first take all of the third person present tense verbs. So in this sentence, we have the verb clean, and we remove its suffix. So here, cleans is changed to clean. Then we insert a marker representing the verb's tense and number right next to the verb. And here the token is S representing singular. We also have a plural variant. And then we tokenize the sentence where the verb marker is represented by its own token. So it'll make sense in a bit why I'm doing this, but it's just so that this control language can be minimally different from the other impossible languages that I'll show. Again, we have the control model's perplexities that we'll use to compare the other languages to. Next, we have the token hop language. So we do the same transformation that we did for the control, but when we insert the marker, we inserted exactly 4 tokens after the verb. And the perplexities for this language were only a tiny bit higher than the control. For the last language, the word hop language, again, we lemmatized the verbs, but this time we place the marker for words after the verb. So we can see that the marker respects word boundaries when it's inserted. And again, it has higher perplexities than the control, but not much higher. So I think since the majority of these impossible languages are almost exactly like English, besides this one difference, a metric like perplexity is only going to show a very subtle difference. So we take a deep dive in these set of languages with a more targeted evaluation.
so in this, sorry, the question.
Yeah.
So for example, your token hop, depending on where you put, like in this example, the tokens do not change, but the tokens might actually like change. Like for example, if you put S, that's like you will have both messy and like messy S, like so token.
That's a great question. So I do this transformation after tokenizing.
Oh,
So that way the corpus has the same exact tokens, just the one difference will be where this S token is placed, so that they're really minimally different, and inserting it before tokenization might do some weird things to the tokens around it, but we avoid that.
So you probably said this already, but for all of these experiments, are you, you start with the pre-trained language model and then
Train from scratch.
Right.
So they only so there's one model trained on word hop that's only seen English that is word hop, and one model trained on no hop that's only seen no hop. Yeah. So all of these are like trained. Yeah, that's what each of these lines are.
So I have a clarification question.
Yeah.
This S token, this is not like just the letter S. This is like an arbitrary singular marker token.
Yeah, this is an added new token to the vocabulary. Since we're training from scratch, that doesn't introduce a problem because the whole embeddings will be trained from scratch as well. Yeah.
There is a little bit of a problem with the token hop one, right? Because you have the it's been too long. I don't know. Standard, is it standard now to have a character to indicate continue or indicate end for segmented?
Oh, like the space before a token, or
the thing that says this is a continue, this is a token that will continue the word when we merge versus.
Oh.
So like books, the word versus books in bookshelf. Those are two different tokens, presumably, right? Assuming books is a token.
I think for GPT-2 that isn't actually the case.
How do they know how to like form words at the end?
This he thing will have like a.
That's what I'm talking about. The thing that says this is a continuation.
Right, for these. So.
Okay, so the thing right, so then what you end up getting is like the thing that says this is, yeah, okay, it's probably I was thinking that you could create like an essentially impossible sequence by like shoving a token in the middle of a tokenized sequence. But it doesn't really seem to affect anything, so it probably should just.
That's an interesting thought that I'll need to chew on a little bit more. Are there any other questions? Okay. So yeah, we'll take a deep dive into this particular set of languages with a more targeted evaluation. And for this, we use surprisals to measure how well each of the hop models can predict the placement of the verb marker tokens. So using surprisals, we aim to answer two questions. First, does the model expect marker tokens in the right positions? The second, is the model surprised when the verb marker tokens do not appear in the position that they're supposed to? And the way we'll do this is by creating pairs of grammatical and ungrammatical sentences for each language where the marker token appears and does not appear. And this will become clear with an example. So taking the no-hop language as an example, what we do is we'll get the surprisal of the marker token in the grammatical construction. So surprisal is just the negative log probability of the token given the preceding tokens. And we'll also get the surprisal of the token that follows it in the ungrammatical construction. And we'll take two measurements. The first metric we use is so the surprisal of the marker token should be small. If it comes to expect the marker token at the right position, it should have a small surprisal. And the second is that the surprisal difference between the marker token in the grammatical case, so and the token that follows it in the ungrammatical case should be large, because it kind of, you can think of it as it got surprised when the marker token didn't appear and it saw the word after it instead. So again, we measure these two metrics across training steps and do this for each of the hop models. So just for reference, these are the three languages. And these are the results for the first experiment that is just looking at the surprisal of the marker tokens. In this graph, we can see that the left bar on each of these graphs is the control model, or the no-hop model. And across training steps, it has the lowest surprisal difference compared to the impossible languages. Both of the impossible languages have higher surprisals. This kind of indicates that they're worse at predicting the marker token at the right position. The interesting thing that I will point out is that counting tokens or predicting the marker when the rule involves counting tokens was easier than doing it for counting words. So word hop is on the right-hand side and token hop is in the middle, and you can see that token hop is better across all internals of training steps. In the appendix, I have a version of this experiment where the models are trained with no positional encodings, and that difference kind of disappears. So that was an interesting finding, that this might be just, this concept of counting tokens is aided by the absolute position encodings of GPT-2. But that's aside.
Wait. So if you have no positional encodings, then you're just coming across a bag of words.
It's not exactly a bag of words because of the autoregressive language modeling.
Because you only attend to the words that you see.
Yeah, at each step, it's kind of, you implicitly know that there's 2 preceding words, and then next step is 3 preceding words. So it does encode order to an extent. And the second experiment is taking this surprisal difference between the word that follows the token and the token itself. And the control model, again, is best across all intervals of training steps. Here, higher is better in this case. So from both of these experiments, they kind of complement each other. We can see that GPT-2 favors the control, favors the natural grammar rule, but it is also capable of acquiring languages that involve the count-based rule. So the final set of experiments I have are, again, related to the Hop languages. We just wanted to take a deep dive into what exactly the mechanisms were for the models learning these impossible languages. So we use causal abstraction analysis, and this is an interpretability framework for identifying and examining causal mechanisms in neural models. And I'll give some background on exactly how exactly causal abstraction works. In the paper, we use the interchange intervention technique to identify the parts of the model that have a causal effect on the output predictions or like the next token predictions for each of the models. And we use a subject verb agreement task. So just to show how this interchange intervention technique works, you can think of having 2 instances of the same GPT-2 model. So in this case, we have the no-hop model because these are both like the same no-hop model. We're just feeding in 2 different inputs and seeing what happens. So in the basic interchange intervention, you provide 2 different inputs. One is typically called the base, and one is called the source. And here they're only minimally different in just the number of the subject. And we would expect the base to predict the singular subject, and we would expect the source to cause the model to predict the plural subject, which I've indicated up there with the token predictions. So when we do an interchange intervention, what we do is we exchange representations produced by the model while processing the base with the representation created while processing the source at a particular hidden representation to see how that affects the causal behavior, like if that has a causal effect on the output behavior. So here I'm exchanging the second token position at layer 2, and basically while it's processing this layer, I put in this representation and seeing that it caused a change from singular to plural, and that tells me that this representation is important for predicting the marker token. So this can just tell us what parts of the model is being used for that particular output token prediction. And we do an exhaustive search by performing interventions at each layer and token position. And then we report the accuracy, like the interchange intervention accuracy is basically all of our examples originally have a singular subject, but we basically measure how many times did it change to plural. So it's the accuracy if now like plural is the correct answer.
So this is after training.
Yes.
You both decode the man be blah blah blah, the man be blah blah blah, and then just take the representation of man, replace it here, So the only it because it's already encoded, it doesn't affect the future representation through the model, but you only change and so the upper representations, right?
So it will affect the upper representation. It's like, imagine you're doing a forward pass, and then in the middle of the forward pass, I pause and I put this representation from a different model in there.
The B is the B at level 2.
Yeah.
That won't change, but everything at level 3 and above, right?
Yeah. And basically, the difference between decoding the men B versus this approach is that in this B afterwards, the first representation stays the same, and everything from up that changes.
Yeah, that's right.
Are you considering that a change has occurred when the argmax at the decoding level becomes plural?
So I didn't actually use argmax. I just looked at the probability of plural versus singular and saw if there was a change.
Only when the plural becomes more probable than singular.
Yes, but I've done this question before, and I think it wouldn't actually change the result at all, just because.
Always it does either of those two.
Yeah. Yeah, that's right. So
For 0.
yes. Wait, sorry.
For 0, it does those two.
Yeah.
I would imagine for higher hops, sometimes it'll just predict it to.
I think it wouldn't change the result. I can double check it later, but
The overall result, I would agree with you. I would imagine the instance level result, there's got to be some cases, right? Because especially since it's got high surprisal early on.
right. That makes sense. Yeah, we do these I also do these measurements at over model checkpoints. So yeah, maybe especially the early checkpoints might be affected. There's a question.
It does appear to say that this is cultural mediation analysis from their own paper.
Yeah, so these are like vanilla interchange interventions. Yeah, I think that goes by the same name.
So Julie, can you talk more about this interchange intervention accuracy and like, so what is it out 100 like regular accuracy?
Yeah.
Okay. Yeah. Kind of explain that metric a little bit.
Yes. So if I'm just looking at the token predictions for like the base sentences, I make it simple, so they're all going to be singular examples. 100% accuracy would be if it always predicted singular. But now we're doing this intervention and we expect a change to plural. So it's now just plural is the ground truth instead of singular. So it's just like the accuracy if what we wanted was plural.
Okay, and so you're calculating this IIA like at every token and every layer over all of the examples.
Yes. Okay. And then averaging over the examples. So the results actually looks like this. I again look at the models over like training steps, but if we could just like isolate one, just to explain it a little bit more. This is the interchange intervention accuracy. So this is like accuracy of predicting like plural across examples, and I follow the same template. So there's going to be a determiner, a subject, and then a verb token. And yeah, this would be like the accuracy doing interventions at like layer 5, token number 3. So this is for the control model. So basically the tokens right above the subject, or the token position right above, or the subject token position is important, as well as the position right before where the marker could be predicted. So this is kind of common in looking at these graphs, just because the token right before the previous token is just always very important for next token prediction. The interesting thing is when we compare the impossible languages, so like the token hop model, we follow the same template, but now there are these 4 intervening tokens. And it's kind of interesting that the model doesn't really get distracted by any of these tokens in between. They don't have any causal effect. It's kind of like it knows exactly to just look at the subject token and then the token, the previous token always has like an important causal effect on the next token prediction. And this looks very different from like other work that has done this sort of analysis on more like natural linguistic tasks, where like intervening words can be important for like predicting the next token, even when they might seem like only tangentially related. So these graphs just look very different from these analysis that an analysis you would do on like actual natural language phenomena. Yeah, so this was just kind of an interesting deep dive we wanted to do for these languages. Are there any questions? Or I'm basically getting to the conclusion, and we have a lot of time, so there's plenty of time for questions.
So can you, I'm sorry if you already explained this, but can you explain why for the subject token, the dynamic is flipped for accuracy actually going up as you go down layers, while for the fourth token, it's the other way around, where the IIA actually goes up as you go up the layers?
Yeah, so that's a good question. So the subject, we agree that the subject token is important for determining plural versus singular token prediction. It's kind of like the model is not using any information about these four tokens in between. And then we can attribute this change just to like the previous token being important for predicting the next token. Like if I change a representation right here, that at this point, like the model is kind of specializing in predicting the next token. So that change will have an effect.
Another way you look at it, I think, is, so if you literally change the token itself, the TS,
Yeah.
then clearly, obviously, that would cause a change. Right. That would be the contrasting sentence. So if you just change the embedding of it, that's like almost just changing the token itself.
Yeah.
And if you change the one layer above the embedding, that's not that far behind it. But once you get to the top, now you're worried about predicting TV.
Yeah.
Right.
Right.
Versus on the other end, like if you literally replace that upper right token, you basically just like switched your model completely. So of course you're always going to predict the desired token.
And that makes sense. Yeah.
Yes, that's very clear. Yeah, at this point, it's basically just using almost the token identity. Yeah.
Well, maybe it's kind of, so as you, I thought your conclusion was going to be like, I can't learn these impossible languages as well as possible languages, but this is more like saying like, they can.
Oh,
So,
yeah.
on which side of the fence are you?
So yeah, I believe, yeah, or this shows that they can learn these impossible languages. We just show that they're not learned as well as the control. And that's our claim, because we're responding to very strong claims about what language models can do. So if we can show that, at least with some of our metrics, it's worse. Like the surprisal experiment still holds even with this. This was more like seeing that the mechanism actually is just very different from the mechanisms for like natural language. There's like another paper that does this sort of analysis on natural language, and it just looks very different from these.
So it's conclusion that like when you enforce these artificial patterns that's not seen in possible languages, the possible languages are able to pick up on that and ignore correctly, while in natural language, you see these graphs being completely different because we see more colors in the middle where they do actually affect.
Yes, maybe not completely different, but you just see something more complex going on. Yeah. Yes. That's the takeaway.
I mean, increasingly, I would probably have to read the arguments about why LLMs are not appropriate for studying human language, but like the argument seems to be like, well, if you have superpowers, there's nothing to say about language, right? Like this is just a thing that they can also do, right? Like if they also have like X-ray vision, that doesn't mean that they can't be used for understanding language. That's a facile argument because it's not about language at all. But like essentially, it's like, well, I can recognize this language, but I can also recognize this other language. So what? That doesn't have nothing to say about natural language.
Yeah, I also think like the big leap is here, even if they can't understand impossible languages. So what? Why can't they tell anything about human languages?
I do think that I agree with that completely. Yeah, the premise is that, yeah, if they can learn them, they can't tell us anything. We are just trying to figure out, do they learn them as well? Like that was, I guess, what this paper was about, ignoring that, even if they could learn them as well, like why should they not be able to tell us anything about language? Yeah, but we still show that they're better at the control languages. So, all right, I'm going to go to the. Oh yes, so this is for the word hop language. I follow the same template as I do for the token hop language, and the pattern looks very similar. So, yeah, so with all these results in mind, I want to return to the motivation at the beginning of the talk and ask, do language models learn possible and impossible languages equally well? So we make the case that the answer is no. GPT-2 can distinguish between possible and impossible human languages. And more importantly, our paper complements a line of work showing that LLMs can tell us a lot about language, and kind of defends this line of work, showing that they can learn syntactic or more general linguistic principles from data. Since we found that GPT-2 had an easier time learning the possible languages, this leads to the question about what inductive bias of GPT-2 matches natural language. We make the argument that it has to do with information locality, or the property that when parts of text predict each other, they're often close together. And a preference for locality arises in GPT-2 due to the incremental causal language modeling objective. And we see this work as a call to action for research in architectures with different inductive biases that might be better than GPT-2 at finding the possible versus impossible distinction. And this is what I'm currently thinking about and expanding on this work. But still, before we draw conclusions about LLM's linguistic abilities, it's important to state that they are fundamentally different from humans. So for instance, we did see that GPT-2 can perform operations that involve counting tokens. Even though it didn't learn this language as well than the natural control, it could still master this rule to an extent. And even though humans are thought to use units like words or morphemes in our language processing, it's highly unlikely that humans are relying on atomic units similar to tokens, or in the same way that LLMs rely on tokens. But ultimately, tokenization is an engineering choice, so we can always change the way we tokenize or omit tokenization entirely to alter language model behaviors that are heavily influenced by particular engineering choices. So going forward, our paper opens up a new question about how LLMs can help us identify possible or impossible languages. And it brings us closer to defining the boundary between these two classes of languages. And we've made the case that LLMs are clearly relevant to investigations about language learning, or what could be learned just from data, or what sort of innate priors are necessary for language learning. And arguments that they are by design unlimited in what they can learn or incapable of distinguishing possible versus impossible don't offer convincing evidence otherwise. Thank you so much.
I had a suggestion. So this is a good slide actually. So like for all of your, you're basically, you're comparing all of these impossible languages to the base language as a way to say like, what's easier for the model to learn, a natural or unnatural language. Yeah. You might want to consider perturbing the base language in natural ways. So then you have, you can account for like, because it's possible that like perturbation in general is the reason why it's like harder for the model to learn. So if you perturbed it, like some examples would be like you could move the verb to the end. So that would be that would perturb the base language, but it would be a natural language because like we know that like natural languages exist where verbs go at the end. And so it's possible that like for whatever reason putting that verb at the end also gets you a perplexity graph that looks similar to like count-based grammar rules or something, and then at that point you could say, oh wait, they actually are learning natural and unnatural languages like equally. Yeah, just a thought.
Yeah, I think that's a great point, and something that we're also thinking about as we try to design more languages or better languages for testing this, and especially since we're just using English.
Right.
Yeah, that's definitely something to consider.
Cool. Do you have some experiments with different model sizes. I know based on what you described, it seems like a lot of compute probably went into even with UD small, but I'm just curious because some of the perplexity graphs were so small or looked relatively smaller than the other bigger gaps, and whether it's like a sort of a modeling kind of limitation, especially with regards to long-term dependency modeling, because if like the locality thing is a big, thing that you was able to detect or assume as one of the factors that is attributed to, the higher complexity. If the model is able to do like 4 token hops more consistently, well, because of more compute, does that gap completely go away?
Yeah, that's a great question. We only trained on GPT-2 small, and I think it's just, compute was definitely a limitation or a limiting factor for us, just because we're training like plenty of languages from scratch. I'm sure model capacity would affect these results, but I think using a small data set like the LLM, it's more like cognitively plausible, and also using a smaller model is approaching something that's more cognitively plausible. That was kind of more of the motivation we're coming from, rather than a huge large language or large language models for this sort of experiment.
First of all, great talk. I'm really happy this paper exists so that we can ask these questions. I have a question. Look, I'm asking this as someone who had to learn English as a second language. So when I was learning English, an exercise for us was like unscramble these sentences. So they would give us a random order of the words, and we had to put them in the right order of English. And you can, like, I had this thought, like, you can argue, basically, I was sort of understanding and learning this in like random language in a way that at the end of the day, I know what the semantic was and like what the semantic was that wanted to be communicated. And then I just put that semantic in the right English order. Like with this example, I want to hear the take of someone from a linguistics background. Like, again, like I have a problem, like big problem, impossible or not impossible with the second part of the claim and that like big, but like, even if that's the case, like, you can say like, if you throw, especially like with justice fiction, with a high scale, like, it's kind of like when you know the semantic that wants to be communicated, like, even if you throw an impossible language to these models, they can like come up with that structured representation themselves, sort of like take that impossible to that internal representation and take that representation to an impossible like output. That sort of like, you can learn like impossibility by having a consistent internal structure and representation. So do you have any comments on that? And like, if
that's an interesting question. So when I think when a linguist is thinking of possible versus impossible, to take the example of like you learning to unscramble English sentences, like I assume they're written out on a page, and you're able to do like, there's probably a lot more I don't know, I'm not don't know too much about like what a cognitive science or a neuroscientist would say, but there's like other processes going on, and you're able to look over the sentence multiple times in order to do this unscrambling. A linguist is usually thinking about you're listening and you're processing a sentence in real time, and you're producing language in real time, which I think it would be impossible for you to like listen to a sentence, like an English sentence where the words have been represented or presented in a random order and then exactly output the correct sequence. And yeah, to address, I guess like the languages here, like the count-based language, like if I was writing and needed to like put a token at every 4 words, I think I'd be able to learn it eventually, but that's very different from like producing speech or listening to speech. So that's where I think the distinction comes. And I think what linguists want to do is like have language models that more approximate that capability, even though obviously a language model can do these other capabilities that we kind of have when if we're able to like write on a piece of paper and think more about something. But Yeah, we're thinking about like online processing.
Yeah, so I have a question kind of about, I guess, like computational requirements of this work, because you have a lot of very thorough experiments, and you train a lot of models here. So can you talk a little bit more about like what the overall compute cost is? And then I'm also really curious about like compute costs of that, the exhaustive search in the interchange interventions.
Yeah, so the training, we trained a lot of models, so it took a lot of compute. So there were like 15 languages we trained. So we trained like 15 languages and like 5 seats for each one. Off the top of my head, I don't have the GPU hours, but like training from scratch took about like 24 hours for each model. So definitely like the compute was like a big part of the project. Did you have a second part of the question?
Yeah, so what are the like compute requirements for the exhaustive search in the interchange interventions?
Yes, so those are like those are forward passes, they don't involve like backprop. So you can just imagine, I think I had like 1,000 examples, and then you'd have to do over the exhaustive search over all the layers and token positions. So that would just be like multiplying that by the layers and token positions. Again, I don't have the exact numbers off the top of my head.
Yeah, very much enjoyed your talk. Thank you very much. Looking forward to meeting you this afternoon. Quick question, which follows up on the theme that Jake already asked about. So there are some natural, borderline impossible question languages, like German, for example, where you have a phrase word like take off, and where they might be ripped apart, and there might be 20, 30 words in between, right? Or you have other languages like Semitic languages that are hard to tokenize with that kind of 3 consonants, and you just kind of fill them in with stuff in between. Or you have the nuclear with highly equivalent, long words with a lot of assimilation. That's very hard. So that's like one challenge, and then another one is actually more realistic so I work with extremely low resource languages. Most extreme cases, fewer than 1,000 native speakers with very little data, and they don't have spelling standards, right? And so there's a lot of variation in terms of spelling, which might be reflecting dialects, but also just generally consistency because there's no standards. So that makes it very hard. So those are real languages, but kind of challenging for natural language processing. So any thoughts on how they would fit on your scale, and do you maybe intend to kind of explore some of the more challenging natural languages?
Yeah, that's a great question. So we would hope that all the languages could fit somewhere here, because these are like the real human languages that people learn. It is definitely like a limitation of this that we're just using English and perturbing English in order to create these impossible languages. One thing that we're thinking about like is kind of disentangling long distance dependencies that are grammatical or like show up in places that are possible, like cross-linguistically, versus the sort of counting that introduced like a long distance dependency that involves counting, but we were comparing it to like a local dependency. I think it would be great to like start with other languages as a base corpus as well, and then do changes to those languages in ways that can get at like broader like linguistic phenomena than just what is maybe biased toward English. I think that's a great point.
I mean, even you could just measure the perplexity. I mean, different languages have different difficulties, right? So in English, it's not so much the word order, it's a very large vocabulary and, messy spelling.
But then factors like tokenization and all of those things will have major effects. So
your baseline is, English perplexity, kind of it might be interesting to see that for a couple of different languages and see where, some of your cases kind of fit in.
Yeah, I think that's a good point.
So lots of interesting opportunities.
Maybe maybe you made this argument already, but I could see like there's an interpretability perspective from this. Like you define a test where you perturb the text, and it's really a test of what maybe language model rules that what linguistic rules that language models are learning and dependent on. Like if you break word count, if that really severely impacts complexity. I'm wondering, I think Justin was suggesting, trying to do the same tests on larger models, but like even different model architectures, like how kind of trying to learn what linguistic rules are, being learned by language models. I could see that perspective. Is that something you guys are looking at?
Yeah, so we're thinking about like ablating the transformer in ways, seeing what parts will make it better or worse at these languages. Manipulating like there are different forms of attention than like the standard versions that use the GPT-2. Tokenization is another thing that can change these results. So yeah, these are all along the lines of what I'm thinking about for the follow-up. And I think they would fit into like also interpreting, just understanding how the transformer is doing processing. It's important to also say that for like cognitive science and linguistics questions, not just the transform. It's not just about the transformer. Like RNNs for a long time have been like used kind of for these like psycholinguistics experiments. So yeah, we're interested in trying all sorts of things and then just seeing how they make a model better or worse at learning the languages.
So I do have a question because I have a viewpoint saying that it's because natural languages are easier to learn, so that they're optimized in this way. It's like I'm sort of wondering about your take on the causal relationship between learnability and natural languages. It's like to me, it is anticipated that these perturbations makes a harder language so that they're harder to learn. So in the first place, because natural languages should be designed in a way that humans also find it easier to learn, so perhaps they are determined like in advance to be easier to learn.
Yeah, I think that makes sense. The issue of languages being more optimized, I think actually would be in our favor because it's something about the data and not about the learner having these like very strong inductive biases that is actually making the possible languages easier to learn. So like the transformer is a very general learner. It's not like imbued with like linguistic rules in its mechanisms, right? But it can make these distinctions, and that's what we're trying to show. It has more to do with the data. So if human language is very optimized, that would actually like support our take.
Yeah, I also have a quick follow-up question. It's just that in the form of natural languages, there might be tasks involving some of the perturbations or counting anything that the transformer's architecture is not good at. So what is like your take on extending your results to solving perhaps those downstream tasks?
Yeah, so that's a good question. So yeah, definitely things like counting, they're kind of known to be like hard for the transformer to do. I think we haven't thought of like follow-ups on like downstream tasks that might be influenced by these. Again, like going back to the we're trying to make an analog to like human just sentence processing and not like something not more deeper cognitive tasks. So yeah, we're kind of just thinking about the best metrics for just measuring like language understanding.
So I have a question that I guess is like asking you to speculate on like the like cognitive science a little bit more.
Yeah.
So you mentioned that to you and I, like the 4-hop language feels very unnatural, and we could probably learn it, but it would be difficult. Do you think it would feel equally unnatural to a child that was like, raised from birth speaking 4-hop English? I don't know if this is really an ethical experiment to run, but do you think it is baked into our brains, or do you think it is a learned a learned aspect of language?
I think that's an interesting question. I don't think that a child will be able to learn it, but again, we don't have the evidence for that. And that's the cool thing about being able to do computational research, is that we can like train these models from scratch and see what is easier or harder for models to learn. But I just don't think that the child would be able to learn the four-hop language.
But there's two parts of that, right? Understanding it versus, generating it and passing it on to the next generation.
Yeah, exactly.
So you might say, well, this is like an unstable language. And yes, a child might be able to learn it, but it's so unstable that,
It doesn't.
in the next generation, it would naturally, move towards something.
Yeah, exactly. Like, yeah, I think that's a
If you're not a programming language, that doesn't mean you want to talk with other people in a programming language, because there's a lot that goes on into what makes a human language, right? So like, if there's an artificial constraint, so you always have to do this, sure, we can adapt. But like, if we get to just be humans and talk to each other, right? Yeah, whatever governs why we decide to make the various changes that we make, which involves way more than just an API.
yeah.
So
That's
we do have a
exactly right.
question from the Zoom audience
Yeah.
that I want to make sure we get to. So this is from Erica Veras-Doggett, who is at Disney Imagineering Research, is suggesting for a comparison to natural languages. It might be interesting to compare the scale of perplexity, quote, difficulty, for these perturbations to the typology of human languages. E.g., there aren't any known human languages with a base word order of object, verb, subject, but there are human languages that include scrambling. Would the LM also reflect those distributions?
Yeah, I think that's a great question. And I think this just goes back to all the points about like, trying this on other languages or having like other languages as baselines here. And I think that also gets at the point, like we thought a lot about scrambling languages and how those are possible languages. So even it's not entirely like that's why this distinction is like still fuzzy, and we don't know exactly where this boundary lies. But I think there are other regularities about scrambling languages that don't make this thing entirely like our random word shuffle thing. But yeah, that's like a great point, and something we're also thinking about.
Yeah, so we've got about 2 minutes left. Anybody have any like last questions, last thoughts? All right, well, Julie, thank you so much for being here. This was a great talk. I really enjoyed it, and I hope everyone else did too. So thank you so much.
Yeah, thanks so much to Katie for hosting me, and then and it's such all these are really great questions. I have a lot to think about.